My name is Miles Turk, and I'm from Augsburg College, and I've come here today to tell you a little bit about an interesting lab that we've been doing, that we just completed in our lab, in our chemistry lab. And I'm starting off by showing you something pretty cool about scorpions. This will help explain some of the stuff that we'll do. And as you can see, this is a UV lamp, and I am shining it on a scorpion. And as you can see, the scorpion is fluorescing like a green glow. And that's pretty strange. Alright, so scorpions contain a unique capability that they can fluoresce when they're hit with UV radiation. So what causes a scorpion to do this? Well, scorpions are believed to have two different compounds in their cuticles that cause them to fluoresce when hit with UV light. Why they possess these compounds is really unknown. Whether it's for a hiding advantage or if they were used way back when they were first coming out of the ocean billions of years ago, it's not known, and it can be debated for a while. And one of the compounds in the scorpion is believed to be 4-methyl-aluminate-ferron, which is what we are synthesizing today in the reaction, which we'll move into. Alright, so this reaction is used to synthesize. This reaction synthesizes, this one right here, synthesizes the 4-methyl-aluminate-ferron, which belongs to a certain type of compound called clumeros, which is what I'll be calling them for the remainder of the speech, just for simplicity's sake. Alright, so the reaction between this resinol here and the acetylacetone with the presence of an acid catalyst is what synthesizes this clumeros. And this acid catalyst we are using today is called amberlist 15, which is a solid catalyst, which is pretty useful in a green chemistry technique, which I will talk a little bit about later. Alright, so moving forward. So why should we perform this reaction? Why synthesize a compound that makes a scorpion fluoresce? Like, why is that important? Well, this compound only exists in nature. We don't just have this readily at our disposal. So if we're able to produce this compound, we can make use of it. And that goes for more than just this one compound. It goes for any compound out in nature that we don't already readily have. If we have the ability to make it, then we can use it and help ourselves advance further in science. The more things we can make or synthesize or figure out how to do will help us move forward in science. And green chemistry is a great way to save money and materials when performing a reaction, which is why we use them in this reaction. Alright, so one of the techniques that we used to determine that we truly did produce our compound was the use of IR spectroscopy, or infrared spectroscopy. And what this did was, what IR does is it hits a molecule with IR radiation, and it causes the bonds in that molecule to shake or vibrate. And as they shake or vibrate, each different functional group within that molecule gives off a different different amplification, different frequency at which it vibrates. And the IR picks up these different frequencies and puts them on a graph, and we've learned which functional groups go with which frequencies. So we can look at an IR graph and determine what functional groups are in a compound. And since we know the functional groups that we hoped we synthesized in this reaction, we can determine if we created our compound or not. We also could have used an HNMR to help us determine better, but the IR was sufficient enough in determining. Alright, so what we did was I took 3 grams of amberlist 15, a milliliter of ethyl acetate, and 800 milligrams of resinol, and placed them in an Erlenmeyer flask. And I placed them in a boiling water bath clamped to a ring stand in order to so our Erlenmeyer flask was not touching the bottom of the glass, but was still in the boiling water. Alright, so we we left our Erlenmeyer flask in that boiling water for about an hour, stirring occasionally. And after the hour was over and the bubbles had ceased and the liquid kind of turned a little bit darker and almost got, I don't want to say hard or crusted on the bottom, but you could see it was kind of coming together. It was becoming less of a liquid. So then I added 2 milliliters of boiling ethanol to the mixture, stirred it around a little bit, and transferred that into a new Erlenmeyer flask. And the reason I transferred it into a new Erlenmeyer flask was to get rid of the Amberless 15 because we no longer needed that to catalyze our reaction because it was over. And then I did the same thing again. I put 2 more milliliters of ethanol into our solution, started to help dissolve our product. And then we put that on the hot plate and let that reach a boil. Once it reached a boil, I turned the heat off and added hot water dropwise until our solution became cloudy. The cloudiness was helping bring our desired compound out of the solution. Excuse me. And then once it became cloudy, we took it off the hot plate and let it cool down to room temperature. Once it cooled to room temperature, we put it in an ice bath to help it crystallize and to form our solid. And once you could see the crystals really in the solution, we ran that through a vacuum filtration to remove everything but our desired solid. And then the solid that we obtained, we took an IR of it to determine whether or not it was a coumarin that we hope to produce. And so this is the IR data that we produced. I'll just let you take it in for a second, and then I'll start talking. Alright, so the first peak that really stood out to me, which is usually the first peak everyone sees, is this very wide, broad peak at like 1330. And what this shows us is that there's an OH group attached to our molecule. And if you look at our structure, which I've placed right here, you can see this is the OH group, the alcohol. And so that moves us on to our next peak, which is at about 1600, give or take. That's 1595 or something like that. But all of these frequencies in which functional groups lie are windows. If it can be up to here or down to there. And this one is about 1600, and that leads me to believe that there's a benzene ring, which indeed we do see in our product. So that's pushed me even more toward we produced it. And then the last function group that we're really going to be able to see, or it's really going to solidify at us, is this oxygen bonded to carbon bonded to double oxygen, another oxygen. And what that shows us is that we have a carbonyl group. And indeed, we see this peak right here, right around 1400, that shows us that we did indeed form our compound. So, the coumarin was produced, and our IR showed that. And to even solidify it even more, and to show that it does fluoresce, and it could be in the scorpion's cuticles, we shined it under the UV lamp, and undoubtedly it shined just like the scorpion did, just about the same color, slight difference, but not really noticeable. And this helped me really determine that we did indeed produce our compound. And so the green chemistry that we used in this reaction was the solid catalyst, as I mentioned earlier. And how this was used was the solid catalyst requires it so we don't have to do a workup for our acid catalyst, which helps us save materials. And also, the solid catalyst can be reused. And a reusable, or recyclable catalyst means that you don't have to discard it after every reaction, and therefore it'll help you save money in the long run. And also, for this reaction, we didn't use any solvent, which means we use less material and save money. So being able to synthesize a product that is found in nature expands our ability to make use of different compounds. And that's how I believe that's how we move forward in science. The more things we can create, the more ways we can use things, is how we're going to move forward in science. And using green techniques is a good way to save money when doing all these reactions. It'll not only save money, but it'll save resources too. Thank you. I'll open up for questions.